Electrodynamics is the study of electricity that is moving. So now we're talking about electrons flowing, usually electrons flowing, from one place to another. And electron flow is called current. And electric current is defined as the rate of charge flow per time. Here's the equation. The units are coulombs per second, which we call the ampere, or amp, after André-Marie Ampère, a French physicist who, among other things, invented the electromagnet and did a lot of work with electrodynamics. The Regents class uses electron flow. We talk about electrons flowing from one side around to the other. The AP class uses what's called conventional current. Conventional current came about because we didn't know that it was electrons flowing. We can blame Ben Franklin for this. It's not fair to do so, but we can blame him anyway. Had he picked his positive and negative backward, then electron flow would be positive flow. But instead, when we talk about positive current going this way, you can keep in the back of your mind that it's really electrons going the other way, but functionally that doesn't have much of an effect on solving problems, which is what we're going to be primarily concerned with. So how fast do electrons move? There's kind of three answers to this question. First, if you have a wire that's at 20 degrees Celsius, if you've studied any thermodynamics, then you can calculate the speed of the electrons using the root mean squared velocity, and it looks like this. Those electrons are going really fast, 10 to the 5 meters per second. But that's all random thermal motion. They're just bouncing around like crazy, but their average velocity is actually 0. They're just sitting there jiggling like crazy. If you put a voltage across that wire, these electrons are still jiggling like crazy, but they will then start to drift down the wire and they will move as they go. And that drift speed tends to be very slow. It can be on the order of centimeters per second, even less, sometimes a little bit more, but very slow, way less than walking speed in most cases. How fast electrons drift through a metal is going to depend on the type of metal, how big around the metal is, and a variety of other factors. But when you flip a light switch, a light 20 feet away turns on instantaneously, right? Well, the reason why is because all of the electrons start to move at once. It's not like these electrons have to march all the way down the wire to get to the light. There's already electrons in the light. There's already electrons filling the wire all the way through. So as soon as you turn on that voltage, all of the electrons start to move simultaneously, and that reaction is very close to the speed of light. So how fast do electrons move? Thermally, pretty fast. Drift-wise, very slow. Reaction-wise, almost instantaneous. Now, the most common analogy that people use when teaching about electric circuits is water flow. They talk about how a battery is like a pump that can pump water uphill, and voltage is like your height for gravity, and it can cause it to flow downhill. And then you can have resistors, things that get in the way. If water's trying to flow through a pipe and that pipe is packed with loose rocks or is packed with fine sand or silt or various other things, it can resist the flow to varying degrees based on how fat or thick it is and things. And that works really well, but water flow systems is not something that most high school students have a lot of experience with. And so I like to use an analogy of something that you do have experience with, and that's people flow. This gets a little silly, but it works well for understanding what's going on. Imagine you have a big looped hallway, and you pack that hallway with people so that nobody can move unless everybody else moves. So if they walk in lockstep, everybody can make their way around the hallway, okay? Well, at first they're just standing there because they have no reason to move. We need to give them a battery. We need to give them a reason to move. So we say, hey, we'll give you $10 for every lap you make. All of a sudden the whole thing starts to move. If we want a stronger battery, maybe we could say we'll give you $100 for every lap you make, and then people really start to go. Or if you really want to motivate them, I guess, we'll take $100 away every time you don't make a lap in a certain amount of time. That might really get people running around. Either way, we have something that is providing the motive force, the voltage, to cause the people to run around. All right? And then, because this is a cruel science experiment, we decide to put a giant revolving door in the middle of the hallway and make it kind of hard to push. What's going to happen to the flow of people? People are going to have to pile in, rotate the thing through, the next group has to go in. It's not just going to slow down the people at the door. It's going to slow down the entire loop, right? The whole loop is going to slow down. That revolving door might be big, it might be small, it might be easy to push, it might be hard to push. In our analogy, that is what we call a resistor. And if we put in more resistors, we can really cause some different effects. The more revolving doors we put in the way, the harder it is. Every one we add slows down the overall flow, right? But what if we added a second branch hallway with another revolving door and then let it come back together again? People could come up, split, go through both doors, and then come back together. 2 doors is actually easier than 1 door if they have a separate path. More on that later.